You know that sharp, pungent smell that hits you when you open a bottle of cleaning fluid? Or maybe you've heard of smelling salts used to revive someone who's fainted. Well, that unmistakable odor belongs to one of the most important chemicals you've probably never really thought much about: ammonia. But what if I told you that very same chemical is the main reason we can feed billions of people, and that it's also responsible for keeping our food from spoiling? Yeah, it's a whole lot more than just a household cleaner. So today, we're going to pull back the curtain on the simple and visible gas. We're going to uncover its hidden story and find out how it quietly but massively shapes our modern world. All right, so to really get a handle on ammonia's impact, we've got to start at the very beginning. What exactly is this stuff, and how did we even figure it out? The story really kicks off back in 1774. A chemist named Joseph Priestley was the first person to isolate it. He called it alkaline air because of its basic or alkaline properties. But it took a couple more decades and the work of scientists like Claude Berthelot and Humphrey Davy to finally nail down its true identity: a simple molecule made of 1 part nitrogen and 3 parts hydrogen. So, what are we really dealing with here? At its core, ammonia, or NH3, is a colorless gas with that really sharp, pungent smell. But its real superpower, the thing that makes it so useful, is its incredible ability to dissolve in water, like really dissolve. And nothing shows this off better than the classic fountain experiment. It's pretty cool. You've got a flask full of ammonia gas, and it's flipped upside down over water. The second just a tiny bit of water gets in, the ammonia dissolves into it so fast that it creates a partial vacuum inside the flask. That pressure difference forces the water up the tube, creating this spectacular blue fountain. It's just an amazing visual proof of this key chemical property. Okay, so we know what it is, but how do we actually make it? Well, it turns out that making a little bit for a high school chemistry class is one thing, but making enough to feed the entire planet, that's a whole different story. On the left, you can see the lab approach. Simple glassware, perfect for making a small batch. It's neat, it's tidy. But to produce millions and millions of tons, you need the industrial beast you see on the right: a massive, sprawling, complex system of reactors and pipes. The jump in scale and complexity is just staggering. And that massive industrial scale is all thanks to one single invention that literally changed the course of human history: the Haber-Bosch process. It's basically a magic trick that lets us pull nitrogen right out of the air we breathe and turn it into something that plants can actually use. This flowchart shows you the genius of it. First, you take nitrogen and hydrogen gas and you squeeze them under incredible pressure. Then, they get passed over a super hot catalyst. That's the key step, where they actually combine. Finally, the whole mixture is cooled down, which turns the newly made ammonia into a liquid so it can be drained off. And the best part? Any gas that didn't react just gets looped right back to the beginning. It's incredibly efficient. Nothing is wasted. Now, getting this to work is a massive engineering challenge. You need some seriously extreme conditions. We're talking immense pressure, up to 900 times the air pressure we're feeling right now, just to force those stubborn nitrogen and hydrogen atoms together. And the temperature? That's a delicate balancing act. It has to be hot enough for the reaction to go fast, but not so hot that the ammonia you just made breaks down again. And the secret sauce to all of this is an iron catalyst, which makes the whole thing happen at a useful speed. So now we know how to make tons of ammonia. Let's take a look at its chemical personality. How does it actually behave when it meets other substances? Well, the first thing to know is that ammonia is a base. When you dissolve it in water, the solution becomes alkaline, and that's why it performs that classic chemistry party trick of turning red litmus paper blue. This basic nature means it loves to react with acidic solutions of metal salts. For instance, if you bubble ammonia gas through a solution of copper sulfate, you get this really pretty pale blue solid. That's a substance called copper hydroxide, literally crashing out of the solution. But if you change the metal, you change the color. Do the same thing with iron chloride, and you get this distinct reddish-brown gunk. This time, it's iron hydroxide. And one more, with lead nitrate, you get a chalky white solid. So as you can see, you get a different, predictable color for each metal. These color changes are like chemical fingerprints, which makes ammonia an incredibly useful tool for chemists who are trying to figure out exactly what's inside an unknown solution. So, this brings us to the big question: why? Why go through all the trouble of the Haber process with all that crazy pressure and heat? Why on earth do we need millions of tons of this stuff? Well, because it is unbelievably versatile. The number one use, by a huge margin, is fertilizer. The nitrogen that comes from ammonia is absolutely essential for plant growth, and the Haber process is directly credited with feeding billions of people today. Our world would look completely different without it. But beyond that, it's a building block for countless other things, from industrial chemicals and explosives to household cleaners that cut through grease. And it even plays a crucial role as a refrigerant. Yep, for over a century, liquid ammonia has been used in large-scale refrigeration, like in ice plants. It works so well because it absorbs a ton of heat when it evaporates from a liquid to a gas. For a while, it got replaced by man-made chemicals called CFCs, or freons. The problem, as we later found out, was that CFCs were chewing a hole in the Earth's ozone layer. Ammonia, on the other hand, doesn't deplete the ozone one bit. And that brings us to a final, pretty interesting thought. We've seen ammonia go from a mysterious alkaline air to becoming the engine of modern agriculture. But now, as we're all searching for more sustainable solutions for the future, could this simple 100-year-old chemical hold new keys? Maybe as a green refrigerant, or even a way to store and transport clean hydrogen fuel? It's a powerful question to think about.